Hey there, welcome to Learn with Longman. Today we're on a road trip through the realm of chemical reactions. Buckle up as we navigate the factors that can either speed up or put the brakes on reaction rates. I'll be your guide, breaking it down with a roadmap of collision theory. Ready to hit the chemical highway? Let's roll. Let's talk about collision theory. It explains how chemical reactions happen. For a reaction to occur, the reactants need to collide with enough energy and in a specific way. Activation energy is crucial. It's the energy needed to break bonds between reactants so that new products can form. When slow-moving reactants collide, they just bounce off. But if fast-moving ones collide, with high energy, boom, a reaction happens. The right collision orientation is also vital. In our example, each hydrogen molecule must hit an oxygen atom just right, or no reaction occurs. This is easier with small, simple molecules and gets tougher with larger, complex ones. That's collision theory in a nutshell. Let's apply this knowledge of collision theory to explain how a reaction can be accelerated. To supercharge a reaction, think surface area. By breaking down a solid into a fine powder or cleverly reshaping it, you maximize its surface area. Picture this, a mesh instead of a solid metal catalyst sheet, or a powder instead of a lump of solid. Why does it matter? Well, it's all about collisions. Increasing the surface area ramps up the collision frequency between reactants, unleashing a cascade of reactions. Simply put, more collisions means a faster reaction rate. Surely you've noticed that things happen faster when stirred. Take dissolving sugar in coffee, for example. Without stirring, the sugar just sits at the bottom, but give it a good stir and it quickly disappears. Why? Stirring evenly spreads out the sugar and the water, maximizing their contact and thus the number of collisions between the water and sugar, which accelerates the dissolving process. It's not about increasing the speed of the collisions. It's about increasing the number of them. Contrary to common belief, stirring doesn't make the collisions more frequent or energetic by increasing the reactant speed. This is because stirring imparts movement in the same direction to all reactants, and thus collisions are not affected in this way. Increasing a reactant solution's concentration can expedite the reaction process. Concentration, which is essentially the amount of reactant in a given volume, plays a crucial role. When you augment concentration, you're basically cramming more reactants into the reaction space. This straightforward adjustment increases collision frequency, directly influencing the reaction rate. For instance, in a reaction involving magnesium and hydrochloric acid, elevating the acid concentration heightens the number of collisions between acid molecules and the magnesium surface, resulting in a faster reaction. This is observed as more vigorous bubbling, as more hydrogen gas is produced in the same time period. Gas pressure is synonymous with a solution concentration. As a reactant gas pressure rises, so does the concentration of gas molecules. This increases collision frequency and consequently accelerates the reaction rate. Consider the oxidation of iron in air. Elevate the concentration or pressure of oxygen in the air sample and witness the metal burning brighter. Why? Because there are more frequent collisions occurring between the oxygen in the air and the metal being burned. Let's talk about why heating things up is the MVP in the world of speeding up chemical reactions. When you're cranking up the temperature on a reaction mixture, you're giving those particles a serious speed boost. Faster particles means more collisions, and there you go, the reaction rate goes through the roof. But hold on, there's another trick up the sleeve. It's the energy boost that we all need. Heating increases the energy content of particles, ensuring a greater number of the squad has what it takes for a successful collision. Think about the Boltzmann distribution, our way of visualizing this molecular action. When hydrogen peroxide decomposes to form water and oxygen at room temperature, it's a slow process, as most particles lack the energy for the move. But crank up the heat, and it's a whole different game. The distribution shifts. More particles hit the scene with the right energy, and the reaction takes off. So in a nutshell, heating not only increases collisions, but also ensures that a greater proportion of these collisions are successful. Catalysts are wonderful chemicals that supercharge reactions without getting consumed in the process. Take iron 3 oxide in the Haber process as an example. Now, catalysts, much like heating, work wonders through two mechanisms. Firstly, catalysts create an alternative reaction pathway, requiring less energy for the reaction to occur. This can be visualized as a lower activation energy bump on an energy profile diagram, or a leftward shift in the activation energy on a Boltzmann distribution. The end result being that more reactants can hit the sweet spot for successful collisions. Secondly, catalysts act like matchmakers, providing a surface where reactants can cozy up in the right orientation for a collision. Picture enzymes like digestive amylase playing this role in your digestive system, aligning starch and water molecules for a speedy breakup into simpler sugars. So catalysts ensure perfect collisions by reducing activation energy and orchestrating reactants in the right direction. Get ready to tackle some questions from my Teachers Pay Teachers resource on reaction rates. If you find them as fulfilling as a good reaction, check out the link in the video description to snag the full copy for yourself. In this question, you are asked to explain why catalytic converters have the structure described in the introductory text. Think back on what we have just discussed and take 5 minutes to complete your answer. Okay, let's compare your answer to the marking guide. Did you consider the economic benefits to using a substrate and the nanoparticles? Did you identify that these also maximize surface area and then link this to an explanation using collision theory? This is another part of the same extended question. Here you are asked to refer to the catalyzed reaction above to explain how a catalytic converter acts to reduce pollution. Once again, 5 minutes will be needed to compose your answer. Here's the marking guide. You needed to explain the action of a catalyst, both in terms of providing an alternative reaction pathway with lower activation energy, and in terms of orientating reactants. Then these need to be linked to an increased proportion of successful collisions. Make sure you are precise with your answers to these longer written responses, as marks are often left on the table by students who actually understand the concepts. I hope you found this information helpful. Your support means the world to me, so please consider giving it a thumbs up and subscribing for more engaging chemistry sessions.